Morning. Welcome to Krishna's classroom. We continue with our exploration of Lebesgue integral for bounded measurable functions on sets of finite measure. We proved the crucial theorem the last lecture, namely that all bounded measurable functions on sets of finite measure are Lebesgue integrable, and this is the main theorem. Now let us look at the consequence of this. So this is applicable. So the Lebesgue integral is applicable to all bounded measurable functions on sets of finite measure. So let us recall the assumptions. Our basic assumptions are E is a subset of R, E is measurable, and M of E, that is measure of E. This is the basic assumption that we keep. Now we talk about all measurable functions, bounded measurable functions on this, and we prove that it is integral. Now we continue with this and look at the properties, or what are the outcomes. Now if you look at the Lebesgue integral, so you have got this bounded measurable functions. So let me just denote this by x bounded on E. They are all real value functions. Therefore, this collection in fact forms a linear space over the field R. So this is a linear space. X is now, what do we have? What about the integral? So all these functions are integral. So f belongs to x implies integral over E f x's. Therefore, integral over E is a function from x to, that is, integral is a functional on x. Now the usual questions we ask, is it a linear functional? Okay. What further properties are there? So the question that we ask is this: is integral the second question that we ask is this, that is it monotonic? Now this question has been provoked by what we have proved for what are called simple functions. Now we have seen that Both these questions have an affirmative answer if we restrict to simple functions. On Therefore, we expect it. So, expect these questions to have an affirmative answer in this case also. Let us prove this. So we have the following theorem. So the theorem that we prove is this fifth theorem. This is on the linearity and monotonicity of the integration. So let us write down the theorem. So let E be the measure of measurable and m of E finite. Let F and G be bounded measurable then for any alpha comma beta belonging to R, so what we prove is this, that for any alpha beta belonging to R, alpha F beta G integral of That is linearity. Then further, if f less than g, then integral over e this is what is called a monotonicity. So the integration defines a integration that is a linear function on x. X we have already defined earlier, which is monotonic. So this is the summary of the statement. Okay, now let's prove this. Let us prove this result. So we observe that f comma g bounded implies alpha f plus bounded. F comma g measurable implies alpha f plus beta g is so alpha f plus beta g is both bounded and measurable. Therefore, by the previous theorem, integral of alpha f plus beta g is defined. Exists. Okay, now we want to look at the linear. So we shall prove linearity. First we prove homogeneity. That is integral of So if psi is a simple function, then alpha psi is also a simple function. The converse is also true. If alpha is not equal to. Now let we split this into two things, namely alpha positive and alpha negative. If alpha is positive, we have taken over E. This is equal to infimum of psi greater than or equal to alpha f. We need to say this alpha f psi. Yes. Now that's equal to alpha times infimum of psi by alpha greater than or equal to, because alpha is positive, so the inequality remains the same, integral over E So we have pulled out alpha, and accordingly you get psi by alpha here, and then this condition is there, and therefore what you get, this is equal to alpha times so that is a straightforward application of definition. Now let alpha be negative, alpha equal to 0, that is negative. Then we have Lebesgue integral is equal to the upper Lebesgue integral which is also equal to the lower Lebesgue integral. The lower Lebesgue integral. Therefore, we will work out this. Now remember, alpha is negative. This is equal to infimum of phi greater than or equal to alpha f phi which is equal to alpha times supremum of less than or equal to, because alpha is negative, this inequality reverses and infimum would become supremum, and you have and this is of course equal to alpha times. So both the cases, alpha positive and alpha negative, this is true, alpha equal to 0, it is trivially true. Okay. So alpha equal to 0. Now this completes the proof of homogeneity. Now what we want to prove is, additivity. Additivity. Homogeneity we have proved, and additivity is what we want to prove. That is integral over E This is done by the usual way. If you want to prove A equal to B, then show that A is less than or equal to B and B is less than or equal to A. The same strategy, because these are numbers. Okay, so we first take up the proof of one of the inequalities, and then we do the other. Easy to. It's not difficult. It's just a routine argument that we make use of. The thing is, you have to keep writing all these things. Okay. So we first know so this is what we want to prove. So for that we will do this thing. So let such that f is right. Then we have now is equal to the upper integral of okay. Now by linearity of integration of simple functions, we have integral over f plus g. Now we can use this one. This is less than or equal to why? Because see, we have assumed this f plus g is less than psi 1 plus psi 2. Therefore, for any psi 1 and psi 2 satisfying these requirements, namely f less than or equal to psi 1, g less than or equal to psi 2, you see that the integral of this is essentially the infimum of this over all such functions, and therefore said if you take a particular element, this is going to be less than or equal. You cannot say that it's equal for this particular psi 1 and psi 2, and this you know is now you take the infimum over all psi 1 and psi 2. That's the next step. By taking the infimum over all such simple functions, we have integral over f plus g. Nothing happens to this integral, but that one, this is true for every psi 1 and psi 2 satisfying these restrictions, and therefore also for the infimum, therefore this is nothing but integral of So one inequality has been established. Now what we need is the reverse inequality. Now you see that you choose simple functions phi 1 and phi 2 such that or integral over E by linearity over simple functions which is equal to supremum See, this part is independent of the functions phi, but this is therefore if this is true for every phi 1 and phi 2. Such that phi 1 is less than or equal to f. Okay. Therefore, it is true for this, and that's equal to integral over f integral over f plus integral over g. Therefore, the reverse inequality also holds. So, these two inequalities imply so that's additivity. Now, combining additivity and homogeneity. We have integral over e of alpha f plus beta g equal to alpha times plus beta times. So that's how you work out the proof of this. Okay. So that completes the proof of this. Now we have to prove one more part, namely monotonicity. So linearity is done. Monotonicity. Assume G. Let by linearity and that's equal to, now h being greater than or equal to 0, h is equal to 0 only. Therefore, implies integral over E G is greater than or equal to integral over E. So that proves it. That completes it. Okay. So we have seen that the linearity and monotonicity extends from simple functions to bounded measurable functions on sets of finite. That's what we have. So the new class, the larger class we have looked at, on that also the same properties do hold. Okay, so it is not lost in the generalization. That's what. So, now we look at some other structure of these things because these are useful and handy for us. Now what we want to prove next is this. Next theorem. Six. Bounded measurable function on a set E of finite. This is the basic assumption on which we are working. Let A and B disjoint measurable. This is important. Disjoint measurable each of these assumptions are important. Okay. Okay, so this is your E. Both are measurable. Okay, they are subsets of E. I am using Venn diagram, not on. Actually, all these things are happening on the real life. Okay, Now, what we observe is this is very easy to prove because you see that take the cutoff of f on A and on B. How do you take the cutoff of A? The cutoff of f on A and B are given by f multiplied by chi A respectively. That is the characteristic function of A and the characteristic function of B. Characteristic function of A is the function that is 1 on A, elsewhere it is 0. Therefore, you see that on A union B, okay, both are measurable, bounded, F is measurable. Since A is measurable, chi A is measurable, so also B is measurable, therefore chi B is measurable. Therefore, you see that these products that you have are also measurable functions. Now, f into chi B. Therefore, hence, to take the integral of this, the integral of this is going to be now use linearity, so you get f which is equal to integral over A now this is exactly what. Okay, so that goes there. Now the next theorem is finite, then modulus of integral of this is a very important inequality which we shall need or we shall prove over and over, or we shall make use of it over and over again. Okay. So that's a interesting theorem or important theorem often used. Okay, let us prove this. I mean, it's easy to do. F measurable on E mod F measurable. This result we have proved earlier. So you write what we have done is F is measurable, then F plus is measurable, F minus is measurable, mod F is equal to F plus F minus. And sum of measurable functions are measurable, therefore you have mod F measurable. Okay, right. Mod F is bounded. That's also clear. And we have minus mod F. This is okay, right. So by and monotonicity of integration, integral over E it is modulus of is less than or equal to integral over or. Now this is an important inequality. Okay, so all these are routine properties of integration that we do. Now we have proved it for Lebesgue integration also, integral also. Now I think that's a place where we can stop for the day, and next lectures or next lecture would look at what is called the convergence of the pointwise convergence of the sequence of bounded measurable functions on E with mu E less or ME less than infinity. So that's what we look at. Okay, we first prove that if it is uniformly, if the convergence is uniform, then the integral also converges. In other words, the interchange of integration and the limiting process is valid. But that, of course, is a harsh restriction, so we would like to relax that if that is possible and explore what happens. And later on we shall see that the famous bounded convergence theorem is proved in this context. Okay, so I think I'll stop here. Thank you very much. So we meet possibly on Saturday. Thank you.